My name is Mark Chang. I'm currently an associate professor in both MSL and FIRST. Today, I would like to give a brief introduction on the work I have been doing recently. And the title is Atom by Atom Construction of a Sub-Nanometer Structures as Highly Sensitive Catalyst. Okay. There's plenty of room at the bottom. This is the very famous phrase mentioned by Richard Feynman. And this phrase ignites studies in small scale. And material in small scale are very attractive, mostly because of their high activity. As you can see in this figure, activity of the materials increase as the size decrease from bulk size to nanometer, to sub-nanometer, and even to single atoms. And 6 years later, in 2021, there's still plenty of room at the bottom because fabrication of single atom material is still very difficult and it's still a very challenging topic. The smallest possible size of a material is an atom, and the activity is expected to be very, very high. Okay, but the high activity becomes a limitation because it also applies to material is very unstable. So in my study, I have developed an atom by atom construction method. It's actually an electrodeposition method to realize precise atomic level manipulation of materials, of metals in atomic level. And generally, there are 3 strategies in my atom by atom electrodeposition. The first one is deciding where the reaction is going to take place. That's the location. The second one is controlling the timing of the reaction to be on or off. And the third one is to restrict the source of the reactants involved in the reaction to make sure there's always one atom reacting at a time. So this is the first strategy, designating the location. This is a conductive polymer, polyaniline, in its emeraldine state. Structural units of polyaniline is composed of 4 benzoyl rings, 2 amine nitrogens forming one half units, and 2 imine nitrogens forming the other half units. And depending on ratios between the 2 half units, we could have different states of polyaniline. And emeraldine state is commonly used in electrochemistry because this state has a high electrical conductivity, and which is very important for electrochemistry. And the other important point is that when emeraldine state polyaniline is used and immersed in a low pH solution in an acidic solution, the imine nitrogens here will be protonated, carrying a positive charge. And because of this positively charged, it could attract negatively charged ions in the solution. So if we introduce a metal complex ions like chloro-ore ions into the solution, these negatively charged chloro-ore ions will be attracted to the protonated imine nitrogen, as shown here. Okay, and because of the charge ratio of the protonated nitrogen and the chloro-ore ions, there's always only one chloro-ore ions accommodated at one protonated imine nitrogen. So this is how the location is controlled in the deposition. And the second strategy regarding the timing in electrodeposition, the timing can be easily controlled by the potential applied to the substrate. And reduction of chloro-ore ions would occur when the potential is more negative than plus 0.8 volts. When the chloro-ore ions is introduced into a system having the emeraldine states of polyaniline, the coral orient ions will form a complex with depending. And studies have shown that the complex structure is very stable because of the high equilibrium constant. And for reductions of the complex here, the reduction will occur when the potential is at plus 0.55 volts. So simply by controlling the applied potential to be more positive or more negative than 0.55 volts, we can control the reduction reaction of coral orient ions to form gold atoms. The last strategy, control of the source. Each eming nitrogen will accommodate one and only one coral orient ions as shown here. And when we control the applied potential to at positive 0.8 volts, there will be no reaction. So the coral orient ions form, the complex will stay as in this structure. But when the potential is changed to positive 0.55 volts, the reduction reaction will occur to form one gold atom near the eming nitrogen. But then there are still other coral orient ions in the solution, in the surrounding. And these coral orient ions could have contact with the substrate. And because of the applied potential is at positive 0.55 volts, reduction of the coral orient ions will occur to form more gold atoms on the substrate. And this is actually the greatest difficulties in preparation of a single atom material. So let's go back to the situation when the potential is still at positive 0.8 volts, and there's only one coral orient ions attached, connected to the protonated eming nitrogen. So at this point, we can do a rinsing step. So by doing the rinsing step, all of the unbonded coral orient ions could be washed off. And because of the attractive force between the protonated eming and the coral orient ions, this coral orient ions will stay connected to the penny substrate. And this is how we ensure there's always only one metal ion involved in the reaction to form one gold atoms. Okay, oops, yes. So in order to do the rinsing properly while controlling the potential on the substrate at the same time, a flow cell is required. This is the flow cell I use in my study. And this is where the reaction comes in, and here's where the reaction goes out. And here's a description of each steps involved in the electrodeposition. So at first, we would do activation state to make sure the polyaniline is in emeraldine state. Then coral orient ions will be introduced into the system. And because of the attractive force between the eming nitrogen and the coral orient ions, there will be only one coral orient ions attached to the eming nitrogen. And by doing the rinsing step with a 0.1 molar concentration of chloruric acid, all of the unbonded coral orient ions will be washed off. Then we simply sweep the potential to minus 0.2 volt to initiate the reduction reaction. And in one step of the reaction, one gold atom will be formed. And by repeating the step, we can control number of gold atoms formed near the eming nitrogen. In order to show strengths of the atomic gold decorated polyaniline, I have used it in identification of normal propanol and isopropanol, because these two propanols have very similar structures and identical molecular weights. And here are the results. You can see that the yellow line is with no gold, and there's no current response from the oxidation of the propanols. And when we increase the number, the gold number to one gold atom, the current response is still very low, indicating this is not active. But when we have two golds, the current response significantly increased, indicating it's very active. And one point we can see that the current response between normal and isopropanol are different, indicating that the catalyst electrode is capable to distinguish between the two isopropanols. And this even effect is to some degree similar to the Crompton effect, So yes, let's do a lot of work I need to do in this study. So thank you for the attention.